I am Michael Barker from the University of Wyoming, and I'm the director of the education for the Short Span Steel Bridge Alliance. And of course, I'm the host for the webinar series here through the University of Wyoming. So following John's pricing study, the second present today is on the economy of steel bridges, considering first costs again, like they did, but then also life cycle costs. And so here's the plan for the presentation. I'm going to go back and we're going to talk about the Short Span Steel Bridge Alliance a little bit more, its purpose and its functions. Of course, one of its functions is to represent the design and construction of simple span steel bridges. As part of that, we're going to look at cost competitiveness of steel bridges for first costs and life cycle costs. Short Span Steel Bridge Alliance is that industry support alliance that is a group of bridge and buried soil structure industry leaders who have joined together to provide educational information on the design and construction of short span steel bridges. The purpose is to help owners and design engineers with designing and building simple span steel bridges. The alliance was formed to address two main concerns with the construction of steel bridges. The first is a misconception across the United States that for shorter span bridges, concrete is always less expensive. And John just showed you that it wasn't, but there's this misconception that they are. The second issue is that a concrete bridge is pretty easy to design using charts and tables, whereas a steel bridge design is an individual piece of art for each design. Now you saw eSpan 140 that helps us with the design aspect, and today we're going to talk about the economy. The Alliance has developed economical studies that address the first cost and life cycle costs of steel and concrete bridges that show both steel and concrete bridges are competitive, just like John's study. The goal is to break that preconception that concrete is always less expensive. And we're going to look at these studies here. And of course, the Alliance has also developed the standard simple span steel bridge designs for bridges up to 140 feet, so that when an owner and engineering is considering the design for a short span bridge, the steel design and concrete design can be quickly developed and compared without the effort of designing the steel bridge. And we saw that eSpan 140 just a couple days ago in Greg Michelson's webinar.
Oh, there, Dr. Barker, your slides weren't moving, but they are now. Sorry.
Oh, okay. So we're going to start with that preconception that concrete bridges are less expensive than steel bridges in the short span market. Many owners and engineers believe this to be true, and many times steel is not even considered when there is a short span bridge need. And this is unfortunate because that means owners may be paying more for their bridges than is necessary. If owners and engineers would compete steel and concrete bridges, the cost for both would be lower due to the competition. Because studies show that states or regions that do not even consider steel alternatives and only build concrete bridges pay more for those concrete bridges than states or regions that have a healthy competition between the two bridge materials. And we will now look at case studies of county and state bridges. The first case study is from Audrain County, Missouri, the year 2012. These two bridges were built by Audrain County work crew, so there is no contractor for the bridges. This is a special case study in that the Alliance worked with the county engineer from before construction through the opening of the bridge to track costs. The steel bridge on the left here consists of 4 steel girders, 47.5-foot span, 24-foot roadway, and a 2-foot structural depth. The concrete bridge on the right consists of 6 precast hollow core slabs with a 50.5-foot span, 24-foot roadway width again, and again a 2-foot structural depth. These two bridges were built in the same year and are nearly identical except for the small difference in the span length. The engineer was asked to keep a detailed account of the cost for the construction of the two bridges so that a direct comparison could be evaluated. This shows the total cost for the two bridges, where the costs are broken into material and labor, equipment, guardrail, rock, and engineering. And we can see that for the total cost for these two bridges, the steel bridge has a 19% savings over the concrete bridge. The costs are calculated based on the square footage of the deck area for an equivalent comparison, since the concrete bridge is 3 foot longer. However, comparing only total costs can be deceiving given the different site characteristics of the two bridges. For instance, we see here that the concrete bridge had significantly higher engineering costs and lower rock costs. So the engineer was also asked to separate out only the superstructure costs so that an equivalent direct comparison could be made for the two bridges. These costs represent the costs associated with only the superstructure. So, as John said, and I think very true here, this is a true apples to apples comparison of the costs for these concrete and steel bridges. Removed from the total cost is all site prep work, grading, engineering, rock, abutments, and so forth. And we can see the cost for the materials, labor, and equipment for only the superstructure. Steel bridge cost came in at $37.54 per square foot and the concrete bridge at $50.61. The steel bridge is considerably less expensive for this comparison. Now, one item to note is the equipment cost, where the steel bridge used a county-owned 30-ton crane. The concrete bridge girder members are heavy, and the county had to rent a 100-ton crane at a cost of $3,500. The other $500 for each was a rented skid steer for incidental work. However, even if the county needed to rent the 30-ton crane, that cost would have been about $1,500. And that increases the steel bridge cost to only $38.88 per square foot, still considerably less than the concrete bridge costs. Now, the steel girders are weathering steel that requires no painting, and these costs are already in the cost of the steel girders. If the county needed additional corrosion protection and used, for instance, galvanizing, the cost would have been approximately, at that time, 22 cents per pound of steel, and the steel bridge cost would still be significantly less than the concrete bridge costs. So for these two bridges, as they were built, the superstructure only costs show that the steel bridge option would have saved over 25% compared to the concrete bridge. That is 5 steel bridges for the cost of 4 concrete bridges. This is for two almost identical bridges where they have the same structural depth, which means no difference in approach work, the same roadway width, the same guardrail system, the same abutments, and the same county crew built both bridges. So this demonstrates that steel is competitive with concrete, and the preconception that concrete is always less expensive is incorrect. Steel short-span bridges can, and many times will be, less expensive than a concrete option. Now, the reason for these economies for steel bridges vary over the bridge fabrication and construction process. For instance, we saw that one reason steel is competitive is that equipment requirements are less, since steel bridge components are considerably lighter than the concrete components. For steel bridges, the dead load is significantly lighter, and lighter abutments can be used. Or some of the economical modular abutment systems can be employed, such as geosynthetic reinforced soil systems. Another benefit for the economy of steel bridges is the use of partial depth precast panels or corrugated metal deck systems that make the casting of the concrete deck efficient. Now, we know steel is a versatile material and that steel bridges can be made in many forms with complicated details in fabrication. However, as John just said, these simple bridges do not require complicated stiffener and diaphragm details. Simple details are cost-effective and easy to fabricate and erect. Another costly component for bridges are rocker or pot bearings at the girder ends. For these simple bridges, simple elastomeric bearings can be used, and smaller bearings used due to the lighter weight of the structure. And of course, jointless decks with integral abutments leads to much lower deterioration rates and maintenance costs in the future. Finally, one of the costs for steel bridges is corrosion protection. Since of course, unprotected steel will corrode. However, weathering steel, when applicable, is low cost and requires little maintenance for long-term corrosion protection. If weathering steel is not applicable, galvanizing, metallizing, painting, or even the use of stainless steel may be a cost-effective method for corrosion control. So that was one example. The Alliance also worked with that same county engineer on other bridges built near the same time frame. This table looks at the total constructed cost of an additional 5 steel and 4 concrete bridges built in Audrain County. At the bottom of the table, we see that sometimes steel is less expensive and sometimes concrete is less expensive. This is healthy competitiveness and is good for the owner. These are examples of county bridges that show that both steel and concrete are competitive in the short span market and should be considered, and both should be considered. Now we're going to go from the county level and look at a couple state bridges also in Missouri. Again, here are 2 nearly identical bridges, one steel and one concrete, that cross over the same highway near Columbia, Missouri. Both are 2-span with a concrete bridge just a little longer and wider, so the total cost will be divided by the deck area for comparison. These were both design bid build projects with a contractor constructing the bridges. Here are the costs for the 2 bridges. Now, both had non-bridge items such as a conduit system, a pedestrian fence, and an architectural facade, and these costs were removed, shown here in green, from the total cost since they are not structural. We see that the concrete bridge came out to $77.71 per square foot, and the steel bridge cost $72.94. However, there was a 5-year difference in when these 2 bridges were built, with the concrete bridge being built in 2011 and the steel bridge built in 2007. So to account for the age difference and inflation, an Engineering News Record construction cost index of 2.7% per year was used to bring the cost of both of the bridges up to a common year of 2017. And we see that the steel bridge was less cost at $85.58 per square foot than the concrete bridge at $91.18. So why did we do that? Because from what we have seen here, and with many more examples not shown here, we see that that steel is competitive with concrete bridges in the short span market, and that owners and engineers should consider both materials for their bridge needs. That preconception that concrete is less expensive than steel in the short span market is a misconception. Both steel and concrete are competitive, and competition is good for the owner and the public. But first cost is just that, the cost of putting the bridge in place. Responsible owners are also concerned about future maintenance costs and service life. The question about life cycle costs routinely comes up. Well, what is actually asked is, which type of bridge is best for life cycle costs? And both the steel industry and the concrete industry have offered anecdotal evidence, but has not, until now, I like to say, had good evidence on which bridge type is best. So a study was conducted that examines the historical life service, meaning performance and maintenance, and historical agency life cycle costs, meaning the true cost for building and maintaining the bridge over its life, of steel and concrete bridges in Pennsylvania. A historical study was conducted so that the results show what actually happened to the bridges instead of anecdotal guesswork from the steel and concrete industries. The Pennsylvania Department of Transportation had good records on their bridges and offered PennDOT data for the study, and we certainly thank them. To determine a life cycle cost for a bridge, one needs to know the full history of that bridge. This includes the initial costs in the year it was built and all maintenance that occurred over the life, including department and contractor maintenance, and the lifespan of the bridge or when it will be replaced. Of course, all of the bridges in the PennDOT database were still in service. So an end-of-life model is needed to estimate the life of the bridge. The study's objective was to compare life cycle costs of typical concrete and steel bridges. So there were criteria that each bridge had to meet to be included in the study. The criteria included considering only typical steel and typical concrete bridges, where that was selected as precast I-beam, precast boxes where the boxes were adjacent to each other, precast boxes where the boxes were spaced apart, steel rolled beam, and steel plate girder bridges. In addition, both precast concrete became a mainstream construction method, and modern steel design and detailing started in about 1960. So bridges built after 1960 were considered. Each bridge that was used in the database had to have complete records for initial costs and date built, and accurate dates and costs for any type of department or contractor maintenance. And then all costs were based on the PennDOT recorded costs. PennDOT has over 25,000 bridges in their database. Of those, almost 8,500 are of the 5 types considered in the study. And of the 8,500, over 6,500 were built between 1960 and 2010 for a potential study database. When the 6,587 bridges were subject to the criteria, many of them did not have accurate and complete life history information, which left a database of a little over 1,700 for the life cycle cost study. This is over 25% of the potential bridges represented in the life cycle cost study, which is a pretty good representation. All of the 1,700 bridges are still in service. So a bridge life model needed to be developed to predict when the bridge would be taken out of service or replaced. The model was based on the inspection superstructure condition rating, which varies from 0 to 9, 9 being a perfect bridge. And it was assumed that the bridge had a rating of 9 when it was built. So up here on the top right, a deterioration rate was determined based on the condition rating in the year 2014 by the change in rating divided by the years, assuming it started at a 9. With the deterioration rate, the remaining life could be estimated by assuming the bridge would be replaced when the superstructure condition rating became a 3. And the bridge life is the sum of the remaining life added to the current age. So yes, this is a linear deterioration model. During the study, more complicated models were considered, like a bilinear model, because we know at the end of the life they deteriorate faster than at the beginning. But what was found was that it did not make a difference, and it is the relative or comparison between the bridges that was used in this study. So down here in this table, this is the first results table from the life cycle cost study. It shows the average deterioration rates for the 5 types of bridges for not only the 1,700 bridges, but the over 8,500 potential bridges. There is no reason not to consider the ones that did not have full history data. So for this presentation, when these results tables are shown, there will be 2 aspects of the results mentioned. First, the top 2 best performance types of bridges will be highlighted, like down at the bottom right here. For instance, here, steel rolled beam bridges have the lowest deterioration rate of 7.1% of a condition rating per year, and precast spread box bridges is the second with an 8% deterioration rate. The second aspect is the statement at the bottom left that all are similar with none way out of balance. The results show that the deterioration rates for all 5 types of bridges are not far off from each other. There is no one type of bridge that greatly outperforms the others, nor is there a type that is significantly less than the others. And we're going to address this statement. All are similar with none way out of balance towards the end of this presentation. So now we're going to look at a life cycle analysis of an example bridge to demonstrate the work of the study. The bridge is a precast spread box bridge built in 1969 with 3 spans and a deck area of 7,600 square feet. In 2014, the base year of the study, the superstructure condition rating was a 5. Knowing that the average deterioration rate for spread box bridges is 8%, the estimated remaining life when the condition rating reaches a 3 is 25 years. Given that the bridge is 45 years old, the predicted lifespan for the bridge is 70 years. The top half of this slide shows the actual years and actual costs for the initial construction and the maintenance over the lifespan. The actual costs are divided by the deck area for comparison to the other bridges. To compare life cycle costs over the database, inflation has to be taken into consideration. So all of the bridges were assumed to be built in 2014 and all of the costs inflated by the engineering news record construction cost indices, like we saw for that earlier case study. So this bridge in 2014 dollars costs $143.45 per square foot, and the maintenance costs in 2014 dollars occurred at years 19, 40, and 44. The study used constant 2014 dollars for all future costs, since the discount rate considers inflation for the future. Now the life cycle of the bridge can be developed with the dates and costs in 2014 dollars. Using a discount rate from the Federal Office of Management and Budget of 2.3%, that takes into consideration inflation and of the future 2014 dollars costs, a present value cost of the bridge's life cycle can be determined to be $154.49 per square foot by discounting the future costs back to the year 2014. This means that if $154.49 per square foot was put away when the bridge was built, the amount could pay for the initial costs and all future costs for that bridge cycle. However, we cannot compare the present value cost of a bridge that lasts 70 years to a bridge that lasts only 40 years because the outcomes are not equal. One way to compare different lifespan bridges is to use a perpetual present value cost, also called capitalized cost, by assuming the bridge is replaced after each cycle in perpetuity. For this bridge, the capitalized cost is $193.97 per square foot, which means again that if that amount was put away today, it could pay for the first cycle of the bridge and replacement of that bridge every 70 years forever. But what it really means with capitalized costs, we can now compare all of the bridges in the database directly. To further make sure the study compared typical bridges for the 5 types of bridges that had capitalized costs outside of 1 standard deviation from the mean of the bridge type were removed. This is one of those statistical things. This left almost 1,200 bridges of the 5 different types that were used to study the results. Now I can tell you, because I did the study, that removing those bridges didn't change the results in any way. So now that we've got our 1,200 bridges, the bridge database was organized by bridge type in 3 Excel worksheets for each type. The first worksheet was the bridge information with location, years built, number of spans, bridge length, deck area, geometry, and bridge materials. The second was the department and external contractor maintenance performed on the bridge. And the third was the initial and life cycle cost results. Then the studies and a final report were produced from the database of bridges. The report considered bridge life and capitalized costs, where the capitalized costs were studied for several variables as shown here on the top left. Now we're only going to look at bridge life, capitalized costs for the entire database, and capitalized costs for short length bridges as shown in blue. But the full detailed report can be found on shortspansteelbridges.org. An additional study was performed to look at the life cycle costs of galvanized steel bridges, and that report can also be found at the website. For bridge life, the database of the 5 types of bridges show that the rolled beam bridges have the longest predicted life at over 81 years. And second was the precast spread box bridges at just under 80 years. However, none of the bridge types varied much from the others with a 7-year spread. And at the bottom is that statement that all are similar with none way out of balance. A good way to look at predicted life that considers not only the average life, but also the standard deviation of the life is a statistical cumulative density function, or CDF. Now here it is assumed that the data is normally distributed. And with the CDF, the question can be asked, what is the probability that a given type of bridge will last at least 75 years, which is the expectation for modern bridge construction? The results here show that there is a 73% chance that a rolled beam bridge will last at least 75 years, and a 65.6% chance that a precast spread box bridge will. However, it also shows, which was a little surprising, according to the data, there is only a 44.3% chance that a precast I-beam bridge will last 75 or more years. Now, this table shows the results for capitalized costs for all the bridges in the database. Here we see the precast I-beam bridge has the lowest capitalized cost, and the steel rolled beam is second. The table also shows the initial cost, present value costs of all future maintenance, average length, average number of spans, average year built, and average life. And this is where we need to be careful with this comparison. Directly comparing all of the bridges without considering the differences in these variables can lead to misleading results. For instance, plate girder bridges in the database have an average of over 4 spans per bridge, whereas adjacent box precast bridges average just over 1 span per bridge. And of course, number of spans along with average length of the bridge has a significant impact on costs. And John showed that in his study where he divided it up into short, medium, long, and extra long bridges. And in a couple slides here, we will examine a more consistent set of bridges based on span length for a more consistent comparison. And of course, the full report examines these different variables in depth. However, for this full database result, we can use the cumulative density function again to ask the question, what is the probability that a bridge type has a capitalized cost less than $300 per square foot? And the results show that there is a 93% chance that a precast I-beam and an 88% chance that a steel rolled beam bridge have capitalized costs less than $300 per square foot. And of course, this is on the whole database, so all that talk about variables applies here also. So now let's go back to the shorter length bridges. Because the short span steel bridge alliance defines short span as simple spans 140 feet or less. This table reduces the full database to only bridges with lengths of 140 foot or less. It does not restrict it to simple spans, but only by the length. And as we see, there is much more consistency in the average length and average number of spans, which makes a better comparison than the full database results. Here, we see that steel rolled beam bridges has the lowest capitalized cost at $266.24, with precast spread boxes at $272.64. However, there is still that statement at the bottom that all are similar with none way out of balance. Now, the plate girder bridges are a little high, but that would be expected here in these short spans since they are not as economical below about 80 feet. So let's go back to the beginning to that question. Which type of bridge is best for life cycle costs? Is it the precast box adjacent, steel plate girder, precast box spread, precast I-beam, or steel rolled beam bridges? And this is where we come back to that statement that all are similar with none way out of balance. Now stay with me here, but the overall weighted average capitalized cost for the 5 types of bridges is $252.40 per square foot. And each bridge type average is within 14% of that weighted average. Moving down this list, knowing that the standard deviations for the different bridge types range from $48 to over $65 per square foot, or a better way of looking at that is coefficients of variation range from 20 to 25%, means that if they're within 14% of the weighted mean and their coefficient of variation is 20 to 25%, that means that any one bridge type may be most economical for a given bridge project. There is no one type of bridge that clearly beats the others. So the conclusions of the life cycle cost study are: typical concrete and steel bridges are competitive on initial costs, future costs, life cycle costs, and bridge life. For any given bridge project, concrete or steel bridge types may be the most economical. Again, that preconception that concrete is always less expensive is a misconception. And in bold here, owners should consider both steel and concrete alternatives for individual bridge projects. Competition between steel and concrete bridges is healthy for the bridge industry, the owner, and the public. And with that, again, I'd like to encourage you to visit shortspansteelbridges.org to see how the short span steel bridge lines can help you with your bridge needs.